Hi friends, so welcome to lecture 46 on our helicopter dynamics course, and today I'm going to discuss the pitch equation. So this is the third motion. We considered flap and lag in the previous two lectures, and now we look at pitch. And I'm going to focus on the right hand side of the governing equation of pitch, and we are going to focus on vertical flight. I'm Dr. Ranjan Ganguly. So recall that the pitch equation is given in this form. There is the if star, then theta double star plus nu theta square theta, and nu theta was the non-dimensional rotating frequency in pitch. And on the right hand side there was one term which is essentially coming from a spring type of situation, and the second term is gamma m theta bar, which is going to come from the moment generated by lift. So this term m theta bar is the term we are going to look on today, and we are going to use BET to derive an expression for this term. So to do that, we have to focus on m theta here. So to get the right hand side of this pitch equation, we need to calculate this moment m theta dr, this term here, and this is around the feathering axis. So we'll see from geometry that m theta is L into xa, which is the distance between the feathering axis and the AC. And so the lift expression we know, we essentially take the lift expression and multiply it by xa. Remember that this is theta minus phi, phi is up by ut, and u is approximately equal to ut squared. So that's the genesis of this expression for lift here. Now going back to our blade in pitch, we know the blade is in this pitching position, so that's the pitch angle theta, and there are two parts of it, alpha and phi. Phi is up by ut, and ut is the velocity in this direction, which is approximately same as u here because phi is typically small. Now we see here that the feathering axis is somewhere here, the AC is somewhere here. The AC for a typical airfoil in subsonic flow is at the quarter chord. So essentially this particular distance is defined as xa, and that's playing a big role here. So we write down the expression for m theta here, and we expand it. Again, remember we were talking of the vertical flight situation. So ut is rotation speed into r being the distance from the route at which you are currently at. And again, up is lambda into rotation speed into capital R, and then ut is again rotation speed into small r. So with these here, we can write this expression out. And then we are going to try to derive this expression for a more general case of theta is some theta con plus r theta tw, which is a typical linear twist type of situation. So let's take this and plug it all in here, and I'll skip a large number of steps and I'll just tell you that this is going to be this expression theta 0 by 8 plus theta twr by 10 minus lambda by 6 into xa. And that's because this is the expression we had obtained for lift. And so this is very similar to lift. It's simply lift into xa. Xa being a constant number does not play any role in the integral sign. So essentially you get this expression, which is very similar to the expression we got for the flapping equation blade or the flapping blade for the case of linear twist. So go back to those lectures and check it out. I think it's the one before the lecture for lag. So now I have this expression here for the pitch motion, and I clearly know what is this term gamma m theta bar. It's this particular term here. And so the presence of this term totally depends on the presence of XA. So it does require that there must be some distance between the feathering location and the aerodynamic center. So that's the genesis of this particular term. And then you again have a term here. So again here we have assumed lambda to be constant. That has helped us to get these equations and the usual constants in terms of C, A and so on. So I will end this lecture 46 here, and I think we are more or less done with vertical flight with this lecture. And now we are going to make a forward leap into forward flight. So the next couple of lectures I'm going to discuss momentum theory in forward flight, and then we are going to focus mostly on forward flight from now on. So I'll stop at this point. I will see you in my next lecture.